start introduction to integration by parts. But before we do that, let's write some things that we do know. What's integration? This is undoing what? Derivatives. So you think about what differentiates to that. So finding the integral of something means you look for you look to undo the derivative that was done. Okay. What's U substitution?
Undoing the product of the derivative.
Not the product. Undoing what? Chain rule. And what we are going to do today is called integration by parts. And this will be undoing what? Yeah. Then naturally you would wonder, well, is there a way to undo the quotient rule? Well, you can undo it, but it just doesn't have a name. It's just, and you know, quotient rule is really product rule and chain rule together. So just having these two will be enough. Anything that has quotient rule involved, these two are enough. Okay? All right. So let's start with a product rule and see what happens. So let's say you're differentiating x times sine x. If two things are multiplied, you're taught that you absolutely must use the product rule. If you don't, you get the wrong answer. Okay? So the product rule says that when two things are multiplied, you have to differentiate only one of them, keep the other one, plus keep the one that you already differentiated without untouched, so you go back to the original one. But the other one that you did not differentiate, it's now its turn to differentiate. That's what the product rule says, right? And therefore, the result you get is x times sine of x prime equals to 1 times sine x plus x times cosine x. Okay, so that's the product rule. Let's try to find the corresponding integral statement then. So integral of what is what plus c. Okay. What goes in the left side?
The integral of cosine x is sine x.
How do you turn a differentiation statement into an integral statement? They're opposites, right? So what do? You just flip it around, right? So what was the answer now becomes the question. What was the question now becomes the answer. So this is sine x plus x cosine x equals to x times sine x plus c. And in fact, that's how you check whether your answer to the integral is correct or not. Just take the final answer and do the derivatives, check that it's agreeing to the question. Now, so that is kind of an interesting result in itself. But often what happens is that you don't get asked with every part intact. Okay? Often you only get one part of the product rule and you're asked that only. So let's suppose somebody asks, well, it's nice, but I actually want to know what just the integral of x sine x should be. And at first you're like, okay, well, I don't see how we can just select that much. And you might start doing other stuff like, oh, maybe you should just integrate them separately. Would that work? Like, if you integrate x, it's 1/2 x squared. integrate sine, it's negative cosine. Oh, sorry, that is a cosine. So if I just took this much and asked the question, then integral of cosine is sine. Do you think the integral of x times cosine is this thing? What do you think? How would you check? How do you check if this is the answer or not? You just take the derivative, right? Take the derivative. And again, it's the same story. You must use the product rule or it's an invalid answer. And this gives you x sine x. That gives you 1/2 x squared cosine x. And none of these look anything like the question, right? So this must be wrong. And so don't do that, right? This is what some people who didn't study for the exam crammed the night before and totally misunderstand what the object is, and that's how you would fail in class. Okay? Don't do that. All right. So now you, since you're convinced that this requires a more elaborate approach, you stare at this for a long time, and then here's an idea. You break this up into sine x dx plus the integral of x cosine x dx. Right, you can do that, right? You can break up an integral into different parts. You can integrate term by term. And then say, well, since this is equal to this other one, why not just move this to the other side? Then you get an equation, right? And that's a very interesting approach to this. So you have x times sine of x minus integral of sine of x. And then there should be a plus c there, but I can get away with not putting a c. The reason is if you compute the integral, the c will appear anyways, right? So if you see an integral, then you can just get away with not putting the c. And that looks simpler, so this is what I'm going to do. Okay. All right. So what happened is that if you are not given the full product rule, if you're only given a part of it, right, then you can kind of pretend that you had a product rule, but subtract the missing part from it. That's like the vague, very crude way of understanding what's happening here. You don't have to understand what I just said, just like overall, very crudely, roughly what's happening is like you're not given the full product rule, so you're subtracting that part, okay? And we'll return to this idea, so don't be nervous if you didn't understand what I said. Let's just continue and see if it does work. Okay, so you have x sine x minus the integral of sine x is, what's the integral of sine x?
Negative cosine.
Negative cosine. So this is going to be x sine x plus cosine of x plus c. Now, how are we sure that this is the answer? How can we verify? Take the derivative. Again, same idea. Take this and differentiate. You have to use the product rule for the first part. Whereas for the second one, it's just the derivative of cosine, which is negative sine. This is 1, so 1 times sine x plus x times sine x differentiates to positive cosine.
Oh.
It's confusing.
Oh.
You really want to memorize the derivatives only. Okay, so sine differentiates to positive cosine. And now you see that these two cancel, and indeed you get x cosine x. Okay? So what we have done is, when we do this, we actually have done the integration by parts. Yeah. Without me teaching you the method, if you follow this, you've already seen integration by parts in action. But for you to be able to use it, you should actually be given the formula for it. So let's derive the formula for it. And I'm going to give you two formulas. The formula that I like to use and another formula that everyone else likes to use. So somehow, I always have my preference that people don't use. But I like my way. I always think my way is the best. All right, so the first part is, okay, so derivation of integration by parts formula. So what I want to do is I want to take f of x, capital G of x, prime. So let's say you have products of two functions. Then we have to use the product rule, right? So this is f prime of x, g of x, plus f of x times g prime of x. That's just the product rule. But you may be wondering why I'm using capital G instead of lower g. That's because I'm using a convention that capital G stands for the antiderivative of the small g. So that, in my mind, this is what's happening. Okay? So if this is true, what is the derivative of capital G? What is that? If this is true, what is the derivative of capital G?
G?
Small g. Yeah, small g. Yeah. Because that's how we have been doing all the time, right? Yeah. If I have some integral, how do you know that that's the answer to this? You just check that if you differentiate this, you get the original. Right? So if you have some integral, if you differentiate, you get the original integrand. Okay. So now we have the following identity. This will be FG. And we're going to turn this into an integration statement. So can you tell me the integration statement? What's the integral statement? What goes on the left side?
F prime of x, big gx,
Big Gx
plus fx,
and small gx, right? Equals
f of x.
the left side, right?
Yeah.
F of x, capital G of x, plus c. And then we are going to use the same idea that we used before. Okay? See, usually your question is posed as two functions multiplied. So this is the one that you want to know. You want to know what integral of small f of x, small g of x dx would equal to. And then what you do is this integral here should be subtracted to the other side, and just like before, the c will go away, it will disappear. So you get small f of x, capital G of x, minus integral of f prime of x, capital G of x dx. And this here is the formula for integration by parts. Now let's see why.
Professor.
Yes.
I actually had a question about the equation.
Yes.
It says like when you put one times sine x plus x times cosine x minus sine x. You took out both the signs, but one is a positive sine x and one is a negative sine x. So wouldn't that negative sine x be negative 1 then?
I raised it already, so I can't really understand what you're asking. But if you're asking that one is sine and negative sine, they cancel the way, so this is the only thing that survived.
But if it's negative, why wouldn't it be just a negative 1 after that?
One is, it's like, what is 3 minus 3?
0.
Yeah, so there's a sine x minus sine x. What happens?
Oh, I see what you're saying.
Okay, so let me show you how this thing is applied. You have x and cosine x to be the two functions, right? So if you have x times cosine x dx, the right side says the g of x, you only take one of them and you integrate. You see what I'm saying? See, f of x didn't change at all. Only g of x became capital G of x, which means you've integrated the g of x. And that's why it's called integration by parts, because you only integrate one of them. So x cosine x, you choose the cosine x only to integrate. Let's see what happens. What's the antiderivative of cosine x?
Negative sine x.
Positive sine x. Come on, you need to know this by now. Okay, positive sine x, right? And then minus. Let's see what it says next. It says the one that's already integrated, it stays. It doesn't change. It just goes into the integral unchanged. Whereas the other part that you didn't do any integration to, that goes into the integral as a derivative. Okay? So that's the integration by parts formula. So it goes in here as x goes into as what?
1.
1, because x prime is 1, right? So it's 1. And then sine x integrates to? Well, it doesn't integrate, sorry. It goes into in without unchanged, right? And if you write down this thing, that's exactly what we have done before, right? You see that? So we've actually have done the integration by parts. That's what integration by parts is. Okay. All right. Now I want to show you a second formulation, which is adopted by many textbooks. I actually don't know any textbook that has this formula. It would be interesting if somebody found some other textbook that uses this one. But the other formulation, well, still some smaller handful does this. Instead of using G and capital G, because people get confused when they see capital G, they just use small g for this one, small g for this one, but then this will be the G prime then, right? You see what I'm saying? If you say, if you demote this to small g of x, then this will be further demoted to G prime of x, right? So the other form that you may see a lot in some textbooks is this one, but that's still like maybe one or two books. Probably very old books. The most modern books use the following formula. You first say u is f of x, and v is g of x, and that means du would be what? What's du then? Du is f prime of x times dx, right? And then dv would be g prime of x dx. Now if you adopt this notation, then f of x is u, so the left side is u, and g prime times dx is dv, right? So the left side looks like integral of u dv equals to fx gx, so it's the multiple of uv, minus, this time gx is v, but this times this gives you du. So this will be v du. And this is the one that's adopted by most textbooks. So any calculus book you see, you're going to see that one. And because of the way it looks, there's a nickname for this formula. People call this the Voodoo formula. Integrate by parts instead of saying a Voodoo integral. And the reason is if you read V du, Voodoo, that's Voodoo, right? So you can actually read this as like Voodoo equals to UV minus Voodoo. Where the Voodoo is like the nickname for this formula. So the reason this is preferred over this one is it's easier to remember. Yeah. And for people who just remember the formula and then just plug and chug, they like to do this. I like this one because rather than trying to remember the formula, I remember it as steps. So what's the integration by parts? You integrate just one portion of it. In the next stage, the same thing goes in, but the other one that you didn't integrate, you put the derivative. So that's more natural for me. But since I've already shown you this one, let me show you how that can be applied to the same question. So suppose you were given x times cosine of x, and you did you choose u as x and cosine x dx as dv, just like that, right? So that this looks like u dv. And then what you do is you have to figure out what du is, and you have to figure out what v is. Okay. What is du? If you apply d both sides, it's 1 times dx, right? So it says dx. And to get v from dv, you have to find the antiderivative, right? So what would v equal to? Sine of x, positive sine x, okay? And then the right side should now look like uv minus integral v du. So if you put u and v multiplied, it will be x times sine x minus integral of, what is it, v du, Voodoo math, right? V times du, so it's sine x dx. And you can see that this is exactly this one, right? So both of the formulations are exactly the same. You just have to pick your choice. It doesn't matter which one you pick, you will get the same answer. Just pick the one that you're more comfortable with, and then you get the answer.